because yesterday's video didn't save. All right, so the way that you think about buffers are, if you have a combination of a weak acid and its conjugate base, or a weak base and its conjugate acid, it is like the perfect Bonnie and Clyde, right? It can do anything. It can negate an acid added, and whenever we write strong acids, I think it is absolutely the best way to write it if you write it as hydronium, because that looks familiar to you. It also forms water whenever it deprotonates, which makes sense in a lot of our situations. If you add a strong base, and whenever you're writing your actual reaction out for the BDA, somebody at the door? Oh, that's one of my other kids. Yeah, open the door. Writing this as a strong acid in this form, and this as a strong base in this form, would be best, because they will make it'll look like your Kas and look like your Kbs in terms of setting up expressions and so forth. So either when you set up your reactions and do this, you'll actually be doing BDA boxes, because these are actually completion reactions. A lot of times you'll have an excess amount of your buffer component, and you'll have a limiting amount of your strong acid or strong base added. And so what's going to be left over at the end? Say again? Well, so you'll have an excess amount of this, for example, this conjugate base. Strong acid added was your LR, and this was already a buffer, right? What's left over at the end? Say again? The buffer, right? So you just have to find the pH of the buffer after strong acid has negated some of the conjugate base moles, or used up some of the conjugate base moles. So in this case, if you still have a buffer, you can either plug it straight into Henderson-Hasselbalch equation, which is a memorized equation because it's not on your reference tables, right? And understand, how you manipulate it for bases. Or once you recalculate actual concentrations, because what goes in BDAs, what unit? Moles. And so moles is not molarity, so you'd have to take your final or total volumes and divide your moles by your total volume to recalculate each of these components. And you could plug that into your Ka. Remember we manipulated Ka to solve for H plus yesterday? We took Ka is equal to H plus times A minus over HA. Now that's a lot of work because you have to recalculate molarities, then rearrange your Kas, and again you get your pH. But it's totally doable that way, so don't fret. You have a backup plan. But I prefer the Henderson-Hasselbalch. Okay, so I'm gonna let you guys check your work for a second on the ones that you did do. I'm gonna get one of my children started real fast. Check your work, and then I'm gonna talk to you guys on how to do some of these. I need to do, and I'm going to call this set 1 through 9 across from left to right. So this is 1, 2, 3, 4, 5, and so forth. Which ones do I need to do? 3 and 4. 3, 4, 5. 5.
Yeah, 9.
Oh Lord. Okay, it might. No, I'm going to do it this way. All right, so. In the case of what you had in the initial column here this was a weak acid, right? Okay, so I might just redraw this. I need to get another page here. I'm going to talk through the process first, and if I need to actually fully do it, I'll do it, okay? So in column 1, you had hypochlorous acid, yes? Okay. You had was it 0.1 or 0.2? 0.05?
0.015.
Thank you. All right, so this is just a weak acid. If you have a weak acid, how do you solve its pH? Okay, so you use a Ka with an icebox. Solve for X, and X is equal to concentration of hydronium or H+, plug in pH, you're done, okay? So next box had 0.02 molar sodium hypochlorite. Okay, if you have that, you recognize it as a what?
Salt hydrolysis.
Okay, so as a salt, and so you have to do salt hydrolysis with which ion?
The chloride.
Okay, so the hypochlorite, right? So the OCl1 minus is going to act as a great base. Now, salt hydrolysis means you do have to add it to water. So when you come to equilibrium there, what are you making? Right, so the H plus is going to be added to the conjugate base. You make OH minus and HOCl. So if it's acting as a base, you must find the Kb from Ka of the hypochlorous acid you had in part 1, which was like 3.5 times 10 to the negative 8. Okay? Once you set up your KB in your icebox and you solve for x is equal to what in this example? Of hydroxide, and then you can find POH and pH. This is old stuff, this is old stuff. Then you had, this is a great picture so far, and then you had hypochlorous acid and sodium hypochlorite. Yes? Okay. And you had like 0.01 molar of this and 0.1 of this. I don't even know if it's 0.1. Okay. What do you recognize you have here? You have a buffer. How do you know you have a buffer? Okay, so it's a weak acid and its conjugate base in the form of a salt. If you have a buffer, what do you have to do? The equation. There's so many of those. pH equals, okay, negative log of Ka. I'm just going to put pK plus log of, so conjugate base, OCl minus over weak acid. All right, so those molarities don't appreciably change at equilibrium, right? So initial and equilibrium are approximately the same. X is negligible. Plug it straight in. Don't even do an icebox. Okay, so our buffer is going to be now utilized further, but at this point we only had weak acid, the salt individually, and then we have the buffer. So what were their pHs? 4.64. So that makes sense because it was a weak acid. This was a basic salt, so it's basic. But once you have your buffer together, the pH should go something intermediate. Now, that had a lot more of the conjugate base, right? It was like 0.1 versus 0.01, so that makes sense why it's a little higher, because it had more of its basic component than its acidic component. Cool? So you should be reflecting your pHs, make sure they make sense too. All right, so after that, you had a column that was 0.005 moles of hydrochloric acid, yes? And it was added to each of these three situations. So this box here correlates with strong acid and this guy, which is a weak acid. There's no question on how we should find the pH of that. What do you do? Right, you ignore the weak acid. It doesn't appreciably contribute H pluses, so you find pH is equal to negative log of your concentration, which was in 1 liter, so 0.005 molar, and it's about 2.5 or something. What is it? 2.3. Okay. So that's for a strong acid, weak acid combination mixture. Then you had strong acid, so 0.005 molar, or yeah, molar because it is in a 1 liter solution of strong acid, and this guy. Well, at first you're just like, oh, it's a strong acid in the salt. It doesn't react, but it actually does because that salt has a strong way in it. Not just a base. Conjugate base, okay? I don't want you to think of it as a base. It's acting as a base, but it's a conjugate base. So this guy can take that H on and make hypochlorite or hypochlorous acid again. But I don't want you to write it as HCl because I think that sometimes you guys get distracted by the spectator ions. Because this is a spectator ion, it doesn't do anything, it's going to ionize. The chlorine's a spectator ion, it doesn't do anything, it's going to ionize. So if you write it out as we had kind of on that first example I had on warm-up today, what you should realize is this conjugate base will react with hydrogen ion, which I'm going to write as hydronium. I have so many visitors. Oh, not a visitor. This is a member of our community. Okay, we're going over homework. Okay, jump in. So if you write the strong acid as hydronium, it will make your life easier. I hope you're writing down some of this too, because you're going to have the down too. So what's going to form here? HOCl and water. Okay, so this is where I need some space. Give me a second. Just want to delete that. I don't need that. Oh, well, it's all right. All right, so I just need a little space here to actually fulfill this because we didn't get to do a full-out example like this yesterday. Okay, so how much of this do I have in moles of the OCl?
0.02.
So this times 1 liter, so 0.02. Okay, so 0.02 moles of that is present. we had 0.005 moles of my strong acid present, 0 and 0 of those present initially. So over the course of this reaction, and this is a reaction, if you have an acid and a base, even if it is a conjugate base, it will be a completion reaction. It will go to completion, meaning no ice box, BDA box. So we're going to have so much of this reacting, some is left over, some is made. What's reacting? Or what's the LR? H3O. So this is going to be subtracted all the way, subtract, add, and add. So as this gets consumed, I subtracted over here. How much do I have left? 0.015, right? 0.02 minus this, 0.015 moles of my conjugate base. And I have made how much of my weak acid? Sorry, I could fill the D part there, but I'm just moving quickly here. So you have 0.015 moles of your conjugate base. You have 0.005 of your weak acid, because those actually reacted. That's why there was a change from initial, because there was a true reaction, not just an equilibrium reaction. So we have two components. What do we have? We have a buffer again, and the buffer has already negated the strong acid, right? So that's out of the picture. It has adjusted its mole ratio sum, which will adjust the ratio in the Henderson-Hausbach equation. So the first buffer, which it wasn't the same mole, so it doesn't matter. We can't compare that pH actually. Never mind. So when you plug this into your HH equation, you should get a pH. Question?
You would use the Ka of hydrochloric acid.
If it's an acidic buffer and you have a weak acid, use its Ka. Yep. Don't you actually do that Henderson-Hausbach equation? Can we move on? Okay. So the last box here had, just give myself some space, okay? Had this buffer that was already there, and we added 0.005 moles of our strong acid. Now I have 3 components in solution, 2 which was already in the buffer, plus the strong acid. So now you have to choose who are the reactants, meaning who is the strongest attraction for a reaction. Who would that be? The salt's what? Right, so the salt's hypochlorite ion is the conjugate base, which is basic, has the ability to act as a base. This is the best acid in this problem, right? That's a weak acid, this is a strong acid. The strong acid will be forced to react, and that makes sense because in this case, we deprotonate, we make HOCl and water. So this is we have to choose our own reaction because we have multiple things that could occur. But at this point, we have initials for 1, 2, and 3. So we have, and this is going to be a true reaction, so BDA table. How much of this initial hypochlorite do I have in moles? 0.1 moles. Strong acid? 0.005, right? And hypochlorous? 0.01. Okay. So what's going to happen is when you have a buffer, the component of the buffer that its job is to neutralize the incoming acid, or its job is to neutralize the incoming base, it's the one that reacts. That other part of the buffer is still present, but as this reacts, it's going to be subtracting its, the LR's amount, 0.005, but it's adding it on this side. So it does make this acid go away and get neutralized, but the pH is still going to go up some because the basic component gets reacted a little bit, and the acidic component is made a little bit more. So we'll adjust the pH just a little bit, but not too much. That's what a buffer's job is, to keep a pH that's pretty stable. Yeah?
So if you were adding a base, it would be HOCl first.
Yep, so that's the last box, right, number 9. So number 9 is the same buffer, but I'm adding potassium hydroxide. So I would have a different reaction. I would have what Corinne just said, hypochlorous plus hydroxide, because hydroxide is not going to react with the conjugate base, right? They're both bases. It doesn't make sense for them to combine. So this is going to cause a transfer of a proton to make hypochlorite, the conjugate base, and water, and you'd still set it up with your initial, and then do your BDA box. So I will just make sure, after we subtract and add here and we get this final value, on that box we were working on initially, how do I find the pH? You say again? Do I have to find molarity? Yes. So there's a special exception for Henderson Housebach. You don't have to have molarity in the concentrations. You can put moles there instead. So you'll have 0.095995 moles of the OCl, 0 of the strong acid, and 0.015 moles of your hypochlorous acid left. Is that right? 1, 2, 3. Yeah. Okay. So this left after reaction. This was produced, and this will go in. Make sure I did that right. That will go into pH is equal to pKa plus log of still what goes on top. Conjugate base over the weak acid. So that can be moles or molarity. Yeah.
The 0.0995 is just 0.09.
Okay, I thought I had that right. I remember 995 from another problem, I think. So, but still, conjugate base over weak acid goes in our formula here. That last column now, can you guys rationalize how would you do that? How would you do the first one? I don't have it in front of me. The first one is hypochlorous acid and potassium hydroxide. What would you have to do? Because it's an acid and base and they have to react. You absolutely have to react them. And then that is called partial neutralization. Because a part of the weak acid is neutralized, yes?
Mm-hmm.
And you make some what?
Conjugate base.
Mm-hmm. So how do you find the pH of leftover weak acid and newly eliminated conjugate base?
Henderson.
Yes, Henderson Housebach, because it's a buffer. So if yours were a buffer there, question?
Yeah, so for both of these, would you use the pKa or do you have to use the pKa?
All of these I'm using pKa because I have a true acid. So if you have a true acid in your buffer, it will be an acidic buffer. Even if you have more of your conjugate base than you have of your weak acid, like more moles or something, and the pH is basic, it's still called an acidic buffer because the component is a true acid. Whereas on the round 2, if you look at round 2, what do you have there? Those are all bases, right? So those are going to be basic solutions, basic buffers. You find POH. You do the opposite Henderson-Hasselbalch equation, which is POH equals PKB plus what? Say again? Truly, we would call it conjugate acid, right, over the weak base. Moles or molarity could be plugged there. All right, so does that help a little bit with clarifying that for round 2? Okay, I try to give equal weight to both acid and bases because most people spend a lot of time on acids because if you can get the acids, you really can get the bases. But the AP exam, they like to throw bases in there because it's not as highly focused on. So we'll make sure we go over that Monday. Okay, so the last bit of buffers is making sure you can talk about capacity of buffers and understanding that you can spend a lot of time on buffer problems, calculating their pHs and so forth. But what you should be able to also do is do some qualitative analysis where you do some like, okay, I added this, the buffer pH should go up or the buffer pH should go down versus quantitative where you calculate. So on a situation like this is kind of what we just walked through, but I just want to make sure you're cool with this. If you have HCl gas added, so you have a solution that's buffered at 9.05. When you add HCl gas, what happens to the pH? The buffer is currently at 9.05. What happens to the pH?
It drops.
Why does it drop there? Don't say because we're adding strong acid. And so the conjugate base is used up, meaning it pulls the pH more acidic. Okay, so I want you to think past the fact that we added a strong acid, really. Okay, so really, you decrease the conjugate base moles by strong acid addition, and that's going to create a lower pH or a more acidic pH. Do we need to do this? No, we don't need that. We need to do that, I don't think. I have a couple of these started because I wanted to do them, but if I think you're okay, I'm just gonna move on from those. So, how would you set this one up? Let's talk through setup, because if you can set up, you can solve. Just raise your hand when you want to explain it. And Lindsay, if you want to sit in the back room and close the door, we're allowed. Thinky,
You could write the equation and set up an icebox.
can you tell me the equation?
Lactic acid plus lactic acid plus water.
Okay.
Yields lactate and hydrogen.
You have to put your charges. If you ever have to write an association, please put your charges. Okay. And so you have that buffer. You have your molarities given at 0.75 and 0.25. Okay. So it says find the pH of the buffer. What would you do? Or anybody other than Pinky. Say again? Yes, you actually don't absolutely have to set up an icebox because what's going to happen with our X is likely neglect them, and that's where we're making those assumptions that initial is approximately the same at equilibrium because the X is neglected here. So I would read that and go, oh, I have a buffer. Those are pretty large concentrations. Not really a large change in concentration will occur. I'm going to restrict the Henderson-Knox back equation and then plug. So after that, we get the pH. I could actually tell you the pH of this. What's going to happen to pH when we add HCl gas?
It's gonna drop.
It's gonna go down because what reaction's occurring? Maybe hydrochloric acid, which we don't write as hydrochloric acid, we write as hydronium. I can't write this right now, so we write as hydronium reacts with what?
Lactate.
So the conjugate base, right? So yes, you guys are choosing between, because you have both components of buffer present, you'd have to choose the conjugate base to react with that because one, those two ions are likely to attract anyway, and secondly, this is a stronger conjugate base that's going to attract, and therefore consumption of conjugate base would cause pH to go down to more acidic. Do you guys feel like we need to do any more with the addition of strong acid or strong base to a buffer to find their pH? Emma says no. Anybody else? Yeah.
So you do a BDA at the end.
Yes, you do VDA at the end because this is a true acid-base reaction. So we'd form lactate back, or lactic acid back. Where's lactic acid on your body? In your muscles, unless you stretch and do, the next day? It's the dynamic stretching. You get it done the next day so you don't have lactic acid. So this is 0.25 molar in, I don't have the volume. Assume it's in a 1 liter solution if it's not given, something like that. So this is 0.25 moles. This was 0.002. And this would be my LR, this would be my excess, and then I would make extra lactic acid, which was 0.75 moles. And so many of you guys are probably thinking, like, how can I shorten this work some? This is a BDA table, of course. But what you could do is just simply see that this is your LR, immediately subtract from your conjugate base, and immediately add that amount to your conjugate acid. And Nico and me, there's Nick for you. He was like, I think I could do this shorter. I was like, go ahead. So he would do pH is equal to pKa plus log of conjugate base minus LR, because he saw the strong acid and the conjugate base would react, and then a weak acid plus LR, whatever the LR moles were. And that was his way. So, of course, do what works best for you in terms of making sense of things. Okay? All right. Let's keep going here. Okay, so I told you at one point in time I would tell you how to find the pH of a weak acid, weak base combination of a spin of salt. So we're going to get there in a second, okay? So I think we understand now how to identify buffers by their components. And then there's one other type of buffer, and it's actually, it's the dichroic nature of the buffer coming into play. So you have that amphoteric ion like bicarbonate, and that's our buffer within our blood, right? Bicarbonate has two components, so it's going to have the conjugate base 1 and then conjugate base 2, which is the carbonate ion over here. So because bicarbonate can act both ways, it can serve as the conjugate acid or the conjugate base based on what we're talking about. So we might jump into that. It has a really funky way of finding the pH. You can see right here. You don't often see that though, so that's why I kind of just want to push that to the back burner for now. Okay, read this bit of information first, then we're going to do an example. Write down the stuff in purple up here. Buffering capacity is basically almost the final topic for us. Now, take my soup. Oh, hold on. Printed some notes. Hold on. I have a stack of papers. Yay! Pinky's gonna pass these out. Pinky and a friend, because there's 2 sheets here. Okay, there's 2 sheets. Yes, sir. Maybe. And then, all right, there's 2 sheets. For some reason, I didn't copy front and back. I did copy these for you, so you would have a paper copy as well to write some of the stuff down on. Thank you, Pinky and Chloe. You can stretch if you need to while our comrades are passing out some papers for us. Get that lactic acid out.
Yeah. I don't. But pretty sure it is. Really? Yeah. I thought it was no, it's a very common word.
All right, so, and we're back. I hope that we can get through this in about 25 minutes or so. That way, I guess so at this point, we're talking about buffers. Next week, you'll be preparing a buffer. You'll be choosing. I'll give you a pH to prepare, and like I said, you're gonna prepare them for my little flesh-eating virus and so forth, and that's gonna make them, live forever. So the buffering capacity is gonna be something that you have to account for because just like a cup has a capacity, or an environment has a capacity, it can only hold so much information or hold so many species of population. This can only hold so much strong acid or strong base added, meaning it can only neutralize so much before the pH starts to rise dramatically. And the approximation is about 0.05 is what they say is the, after that it's been changed too much. And they base that upon the blood pH because blood pH has to be very stable, has to be very able to accommodate a lot of strong acid and a lot of strong base if it were added. So we try not to go more than 0.05, and then after that it has surpassed capacity. But the capacity is going to be based on the ratio of that last component of the Henderson-Hasselbalch equation, the conjugate base to the acid, or vice versa, conjugate acid to base. And so, not the capacity, the pH depends on that. The actual concentration, meaning the moles present, will give us the amount that we can add. Because once I've added so much strong acid, what's going to happen to the conjugate base? It's going to go down, and what if I keep adding strong acid? Eventually, the conjugate base is going to what? Run out. It's going to be consumed. Do I have a buffer at that point? No. And then I keep adding strong acid. What happens to the pH? Goes down dramatically, right? So that moles that are present, or the moles that are present of our conjugate base or weak acid, they will control the capacity we have. So if you want a buffer with a large capacity, what do you have to do? What do you have to do when you make it?
I'm on conjugate base.
And not only that, but the other way too, because I could also add a strong acid or strong base, right? You don't want a lot of moles of both your components. just because it's a buffer doesn't mean it's going to buffer forever, right? You don't want a lot of moles of them. So down here, I have 2 questions. I want maybe these 1, 2, 3 groups. You guys calculate the pH of this buffer, and then you 4 calculate the pH of this buffer. Go ahead and do that now for me. So how are you calculating the pH of these guys? Henderson alphabet. If you want to plug it in your calculator and tell me, I'm ready when you are. What's the pH of this buffer and the pH of this buffer? Anybody? Go for it, Macy.
I got 4.75.
All right, so anybody else in the 5.0 molar group say 4.7, 4.7 what?
5.
4.75. Can I get a thumbs up from this group? I'll give you guys another minute there. Other group, what's your pH?
4.87.
Yeah, the Ka is up here. Say again.
4.87.
So you're just finding the pH of this and this together at 0.05. Thank you. I thought you said 5.7. Did you say 7.5? Okay, gotcha. Okay, so off the bat, what you guys should realize is I have the exact same buffer here, right? I have acetic acid and sodium acetate. In that formula, so I was hoping maybe someone would be like, hey, it's the same thing. But the formula, pH is equal to pKa plus log of acetate, why is it gotta be so long? And acetic acid. Okay, so the pH is controlled by the acid of choice, or the conditions present, so the pKa, and the ratio of the moles, or the molarity, of those 2 species. Our ratio here is what? 1. It doesn't matter if I have 0.00005 molar, 5 molar, or 5,000 molar. The ratio, as long as I have them in equal quantities, they're 1. So the pH, it better be the same, because I've got the same conditions here. The only thing that's different is what? The amount of moles. Therefore, what's different about my buffer? How long it lasts when I add strong acid or base, and we call that the capacity. Okay, so which has more capacity? A, right? Because it has the ability to adjust for more strong acid and base, because it has 5 moles to work with, whereas this only has 0.05 moles to work with. So if you were trying to have a buffer that would accommodate a large amount of strong acid or base, I would choose the first one. So what happens when I change, or what pH change occurs when I add 0.01 moles of this acid? I'm going to try the Nico and B-Way. We'll try this. How would that change my setup here with my Henderson Hasselbalch? I would have pH equals pKa plus the log of condition 1. How many moles, or what's my molarity of my conjugate base for that A up there? 5 molar, okay. When I add a strong acid, which was, what was it, 0.01, when I add that strong acid, who is it reacting with? The conjugate base or the weak acid? Okay, so what's going to happen to the moles of conjugate base? Right, it's going to negate some of it, so it's going to cancel or subtract 0.10 moles of the conjugate base. What's going to happen as that conjugate base is consumed? To my weak acid, right? Because my reaction is conjugate base plus hydronium yields weak acid and water. So as I consume my base, I'm making acid. So I'm setting it this way just to show you another version of this, because it does get tedious, and I do it all the time. So weak acid here. So what's going to differ in the second example is that our moles here were different, right? Go ahead and plug that in your calculator because you already have the Henderson House by present in your calculator. Adjust that for me and tell me what those two pHs are. Let me know when you're ready. First one. Or second one. I could write the whole formula out if I need to. I'm doing a lot of assuming. Am I assuming too much? What'd you guys get?
4.7.
You guys, did you do this one?
I got the bottom.
You did the bottom one?
I had the same thing.
For this example here, what'd you guys get?
4.7.
Okay, that should make sense. This is a great buffer with a great capacity. So when you add that little bit of acid, it doesn't change the pH by very much. That's the job of a buffer. That second example, though, with the pKa plus log of 0.050 minus this for the conjugate base and 0.050 plus this for the weak acid. What'd you guys get? You get 0.75 again?
4.75,
Yeah, I got 4.5. Okay, I got 568, but I'm just gonna roll with that. So double check that again, that you put that in right, because that should be different. All right, so the goal of this was to prove to you that the capacity, when you add a strong acid or add a strong base, it will adjust the pH. If you have a low capacity, it will adjust the pH more, which we just see down here, than it did up here. Because the initial pH you guys said 474 or 475, so you see this didn't change pH at all. This one changed more dramatically, so we would die if that was our blood, okay, because it would change too much. All right, so that's how capacity plays a role. Can I move on from capacity? Kind of get a look of everybody's faces here. Some of you guys are responsive, okay? If you're not, oh, sorry, let me make sure I talk about everything I need to here. Yeah, okay. Oh, the other factor that I want to ask you guys about is if I take a solution and I dilute it, what happens to the pH of the solution, of the buffered solution? And we have an example right here. Nothing, right? So if I say, what happens as you add a liter of water to the buffered pH? Nothing, because you have 5 molar here and 0.05 molar here. The buffer was diluted, and you saw the pH was the same. But if you dilute a sample so much, the capacity can differ because sometimes you'll have the molarities that differ, and if the moles were the same, you'd be fine. But if it changes the moles in any way, somehow you would then have a different capacity, which the pH would change more dramatically. Well, we'll get you an example with that. We're not quite there yet. All right, so this is the second page. Look in your reading. Just make a star that you need to know the best buffer if you were to prepare one. You guys see this on your paper? Just making sure you got both sheets. Okay. The best buffer that has the ability to neutralize acid, added, and base added would have an equal ratio or a ratio of 1 of that conjugate base to acid or conjugate acid to base. And so the phrase, it improves the ability to neutralize as the ratio approaches 1, might be a phrase that you use if you ever have to explain about capacity of buffers being added, strong acid or adding a strong base. So buffers that are supposed to neutralize acids should have more of their conjugate base. So for example, in our blood, a lot of times we're adding carbon dioxide through inhalation. So carbon dioxide, when it dissolves in water, makes what? Carbonic acid, which is an acid. So in our blood, we hope to have more of that conjugate base, bicarbonate, than some of the other species, because its job is really to neutralize that acid added to our blood. So some buffers have special purposes, is what I'm saying. And so if you have a buffer that's supposed to be neutralizing base more frequently, you have a little bit more of your conjugate acid or your acid in general. Yeah.
Does the pH of the buffer like not changing when diluted have anything to do with like the fact that it has both acid and a base in it?
Yes, because it's the ratio of the acid and base, of the
So, like,
conjugate
if it
acid and
had
base.
more acid than base, diluting it would lower the raise the pH.
Not if the ratio is the same, because that ratio was just the relative amount of conjugate acid to base. And so if you keep that ratio the same when you plug in your Henderson-Hasselbalch, there's no change to your Henderson-Hasselbalch, right? So as long as this ratio, doesn't matter if it's diluted or concentrated, as long as this ratio stays the same, and you're of course still doing the same acid or base, that stays the same, there's nothing else in the Henderson-Hasselbalch to affect it. So diluting does nothing to pH, okay, of a buffer. And lastly, so that's kind of just some notes to self on multiple choice mainly. We have to talk about prepping. Oh no, one more thing. So whenever you're talking about, well, no, this is really good prepping. So if you're trying to find a special buffer that you want to make, and I say, okay guys, I will make a buffer with pH of 5. You have all these acids to choose from. You have to look at their pKa's to figure out which would be the best acid for that buffer. So the example here, and I'll show you the example first and we'll come back up. The example here is which acid would be the best to prepare a buffer of 4.3. What you look at is you want to have a buffer, in this case an acidic buffer, with a pKa that's really close to the pH you want to prepare. Because if you think back to the Henderson-Hasselbalch equation, we have pH equals pKa, right? Well, if pH equals pKa, what's the log of 1? 0, okay? So if the log of 1 is 0, and we always attempt to have our buffers have a pretty equal amount of our conjugate base and our weak acid, because that gives us the best capacity. If that's 1, meaning the overall log is 0, who's the only thing left to control the pH? The pKa, which is just basically the nature of that acid, the extent of dissociation of that acid. So if you have a list of Kas and you don't have pKa's, how do you estimate pKa? Like here. The exponents. Remember we did this yesterday a little bit? We talked about how the exponent is the maximum the pH would be if this were H+, same story applies. The exponent is the max that the pKa could be in this case as well, because we have Ka values. So what would be the best acid if I want to make it 4.3 pH? Might be hard to see these, I'm sorry. Some people say B, and some people are probably looking at C. Okay, so think about how this relates, because it's negative log, right? So pKa equals negative log of Ka. So if Ka is bigger, maybe we can do this by logic too. If Ka is bigger, does that mean it's a stronger acid or a weaker acid?
Weaker or stronger?
Stronger acid, so that means the pH goes down. Okay, so let's write our logic down. If Ka is large, that means a better or better acid, so pH goes down. So which of these two Kas is larger? C, meaning it's going to be closer to the 4 side of things, whereas that one's going to be closer to the 5 side. So which would be best? C. Can you guys double check that with your calculator? Did we already check it? Okay. So that's your logic though behind, because sometimes you're stuck, you're like, I don't know which one. If you think about what Ka truly means, maybe that'll help you decide. All right, so does this make sense so far? And it's based on the Henderson-Hasselbalch equation, but the reading up top gives you a little bit more information for that, so you guys have this reading. But in terms of thinking about this capacity, 1 ratio for the conjugate base to conjugate acid is what that's talking about. And then we want our range, if you're trying to choose the best acid to prepare, it should be within plus or minus 1 of the pKa of that particular acid of choice or base of choice. And then a lot of times, if we're trying to create still a decent buffer, but maybe not a 1-to-1 ratio, Our maximum generally is a 1 to 10 ratio because logs increase by a factor of 10, right? They're log base 10. So this right here correlates with our 1 being our wiggle. So plus or minus 1 because our ratio is going to be between 1 and 10 of our conjugate acid base or vice versa. Whew, I'm sorry I'm talking a lot today, guys. Okay, so I want to make this buffer. First off, using the buffer component we just decided, which was benzoic acid, right? Using that, how much salt do we need to add to 1 liter of the stock solution of the acid that we just decided upon? So you guys said the acid was benzoic. What's that? What was that Ka? 10 to the negative fifth, okay? So I want you guys to decide on how to make a buffer with a salt that has benzoate in it to make the correct pH.
What was the pH?
Sorry, 4.3. I want to write some stuff down on this one because this is going to be great. Maybe put a star by this if you have a lab that deals with this. So if you have a good model, you can utilize your model to solve for your pH in the lab. Talk in your groups. Give you guys a chance to brainstorm first. You guys have benzoic acid's formula on your Ka sheet, right? And you are on board just in case.
Do you want in grams?
Start with moles because you probably want to know the formula of your salt, right? So does anyone want to tell me how they got set up? Let me, before you actually say that, benzoic acid is C6H, yeah. This is benzoic acid. It looks like this. It's what's found in aspirin, I believe. So it's a drug, and we actually take that. But where's the acidic hydrogen here? The only H left. Oh, do you guys know what does this mean? This little diamond here. Yeah, these are carbons, right? This is your organic review. Okay, so those are carbons, and there's H's hanging off of those. They go to C6H6, and that's a resonance structure with the double bonds, and it could go the other way, but I've drawn it this way. This is a what group on the end? What functional group? So we already said this is the acidic hydrogen, right? There's only one functional group that says the word acid. Carboxylic acid, thank you. This is a carboxylic acid. And so it's this H right here that pops off to form the acidic component. So, and you'll see this like in amino acid structures. They like to scare you guys with organic, but really, if you understand and you're not scared of the picture, you can move on with the problem. They throw a lot of organic structures on the test. Okay, so how did you guys start? Who's confident? Let's get a combination of you two. AJ and Minky.
So you write the Henderson equation and you plug in your gibbons. So what do you know?
Conjugate base over weak acid, okay?
So you can plug
So
in
what do you know?
everything except for the conjugate base.
Okay. So you're going to do like 4.3 equals negative log of, was it 6.4 times 10 to the negative fifth, okay? Plus log of x over 15.
Mm-hmm.
Okay.
Then you just solve it.
Okay, so when you solve for x, how much you get? Do I need to solve this mathematically out right now? We kind of did one like this yesterday where you take your pH minus your, or plus your pKa, I guess, on that side from this, and then take your log, and then inverse of log is 10, so you raise it to the 10, or 10 to the log power. Solve for x, what do you get for x?
Like 20.1 moles.
How much?
20.1.
Hold on. I got 19.2, thank you. Okay. Can anybody else verify that math? I got 2 people. I'm just going to make sure you can plug this in your calculator. I actually, I went ahead and just took my pH minus my pKa, and then I set this as x in itself, and then I actually, in the end, multiplied by 15 to get the original x. So, but make sure, give me a thumbs up if you got like around 19.2. Do you verify that with yourself? Because, I mean, you guys are calculator savvy. Make sure you know how to use your own calculator. All right, so this is our moles of conjugate base, and so what would be a conjugate base of benzoic acid? It's benzoate, but we would need a salt with that, right? So what would be a salt with benzoate? Say again? Sodium benzoate, right? Something, because what you should realize, and I drew this with that purpose, if this H pops off, what is the charge of this? -1, so it has to be a cation that bonds with it. So sodium benzoate would be the maybe a good example of a salt, and then you take the moles 2 grams. Okay, so you guys will have ones that you are more familiar with than benzoate for your labs. Okay, so and I will tell you, I used potassium benzoate. If you used potassium benzoate, you multiply by its molar mass, which was 161 grams per mole. That gave us, like, get ready, 3,093 grams, OMG, of our potassium benzoate, right? There's no way in hell I'm going to give you that much salt to put in your buffer. There's no way. So and I'll give you a capacity, I'll give you a solution pH, and I'll give you an amount that you can use. You cannot put more than you are allowed, because some of these things are very expensive, right? And we always want to be environmentally conscious. So that 15 molar solution, you wouldn't have to make a liter of the 15 molar solution. Maybe you could make 100 milliliters, so we at least pop it back 1 decimal, which would limit that down to 309. So we would have to make sure that we're using all the conditions present. Okay, and then I think that you guys are good to go. I want you guys to do the questions that are on this slide, which I believe is on your 6th. Let's see, it's on the 6th page. Which other page? Oh, right here, sorry. Okay, so it's down on the lower, no, it's up on the upper right-hand side. I want you guys to work in groups for maybe 15 minutes, solve those, and then I think we're good for buffers and buffer tests.
So you're
I mean, it's usually making you do a base because we haven't done a base yet.
acid? No. Yeah. So you're trying to base which is and then this was the HCl.
pKb of ammonia, if you need to write that down, is 1.8 times 10 to the negative fifth. It happens to be the same pKa as acetic acid. So you've seen that one before.
Or is that KB or PK?
I mean, sorry, that's Kb. Sorry, pKa is like 4.74.